Hello, this is Op from the Start. I am, in a way, I guess, somewhat reacting to a video by Stand Up Maths, in which he has a discussion on a particular way he has come up with a equation for a triangle, and I want to discuss my own take on same problem from a different angle, and how I believe mine is at least a little bit better. It's also worse in some way. So from the video, he talks about how he uses the sine function as well as the sine function multiplied as long as the equations for the lines of the triangle to create a triangle in 3 lines like this. You can move it around. It all works fairly well. The one issue I have with it is that it is a very long equation, and while each part is intuitive, if you were to be shown the entire thing, I would say it would not be as much. And the other problem I have with it is where it starts to break down, as shown here. It has some breakdowns that are expected, like when the triangle doesn't contain the origin, since it relies on that fact. However, certain cases where, say, one point is just like on the wrong side of another point, it will mess up, so that if you would switch the points around, you get stakes that aren't reflective of an actual triangle. So the method I use to attempt to make equation for a triangle and so on is from another video that he had made, in which he explored what is called a squircle. And so if you see here, the area made here is a circle, but as I increase the exponent on this equation here, it begins to look more and more like a square. And so this is what is known as a squircle. Even though the corners look straight, there is a small amount of curve, so this will never actually be a perfect square. However, it is a good base to look off of. If you play around with what's inside these exponents, you can see if I do x plus y instead of just x, you get this slant here, which is a 45-degree angle, which would make sense since you have a point 1 up, it's here, 1 along x, 1 along y. It forms a 45-degree angle here, and so it will form 45-degree angle perpendicular to it the other way. And so one day I was thinking, what if you were to add a third term? Let's say it's 45 degrees in the other way, so x minus y, which would be here. This doesn't show up well. Yes. And now you see this one is causing this, since this is corresponding to a line that is like this. It forms this side. This one is a line along y, so it's forming these sides. and the last term is forming the other side. And as you can see, this is it's not a regular hexagon, but it is a hexagon. But unfortunately, a hexagon is not a square. So I had to do something a bit trickier, which is instead of using just a polynomial, I had to use a modified polynomial which looks like, which is not quite a polynomial. If we take this to smaller values, we can see that it starts from 0 and onwards. It is in fact a polynomial, but from behind 0 it doesn't do anything. And so that makes it so that it'll only emphasize one side of it. And as you increase the exponent, you can see this sharp angle that you need in order to actually make a shape. And see, let me change this up. Oh yeah, this one of these needs to be, nope, probably the other one. Okay. Yeah, I didn't really plan this one in advance. Which is on me. You can see with this, it now does form a triangle shape. And so I used the information from that to make this graph here in Desmos, which, as you can see, when I drag these points around, you can get all different shapes of triangles, but no matter where you put them, even here, it is still a triangle. It doesn't do the weird things that the other one did with having 3 sides that go off to infinity. And yeah, so this triangle, I just have this, instead of paying attention to its angles from the center, it pays attention to the angle of the average of these 3 points, just so it doesn't do anything weird like it was doing before. But what's good with this example is that by changing almost nothing, you can also add a 4th point, and this also, you can move it anywhere, you can switch points around, and as you can see, it still remains being a quadrilateral. And so you can take this up. One thing I found interesting is if you actually take it the other way. So here I have a graph that just does the regular shapes of each. Like this is a regular triangle, do next regular square, regular pentagon, and can generate all the regular shapes. What I find interesting is, since this generalizes, this is what it would call a general two-gon, which in this case is just a band that stretches on for infinity. And in fact, I believe that this actually does qualify as a two-gon, but it's just a bit, this isn't quite the correct way to visualize it. And so I'd say that the actual extension of the two-gon is this band.
not as a three-dimensional object, but as its surface. It is a two-dimensional object in that, as you can see, if you imagine the paper would have no width, this would be purely two-dimensional. As you can see, it has two sides that do not bend in their respective two-dimensional way. If you were to follow these sides, you would say that they were straight. And it has exactly two sides. So this would be the two-gon.
And so that was the two-gon. And so now let's look at what it supposedly says is the one-gon. And in this case, it is just a straight line, or it's not the straight line, it is one entire half of the plane. And I would argue that this is somewhat equivalent to being a circle. So yes, a circle is a one-sided shape. Say that since, as you can see, it splits the real number, or splits R2 into two separate groups, and there's no way to get out of it, and anywhere, no matter how you look at this, it is basically a straight line. If you would take a surface of a circle, it would also appear to be an infinitely straight line. Difference is curvature. I don't really know how to say anything about that, but essentially I think that they are similar enough in this case to be equivalent. And in the zero case, the way I've been doing this breaks down, but this essentially simplifies to the sum of nothing, which would just be 0, is less than or equal to 1, which is true for every single point, and so the zero-dimensional point is just the entire plane. So that is my equations. The one concession is that as for how I've done this, it still is technically not triangle, since obviously it will always have the rounded corners, but it does solve a couple of the problems that are caused by the former way of doing it using non-continuous functions. So I improved my graphs a bit. Before, when I was using it from 0 and so on, it would still not have perfect corners. So I was thinking about it, and I figured out that if I would use something like this square root, where on one side it is completely positive, and on the other side it isn't defined, or at least not defined in the real numbers, that it would end up making perfectly straight lines. This, like, you saw it, where it clips off the corners. That's just part of how how Desmos works itself. Yeah, so now instead of having that exponential function that looks like a corner, I'm using 1 minus square root. With this, perfect lines, it still works perfectly as before. And we look at this one, and we can see in this case all of these are the same, except they're actually exactly the shape they're supposed to be. This is still the band. This is still its half of the plane. This is the entire plane, but it doesn't show up. And yeah, I would like to explain what I was meaning with, like, So I was saying that this is basically a circle. And yeah, I didn't do a very good job explaining it. So basically what I was talking about, if you take it from this, you take it to be polar coordinates. If you take the exact same equation, you end up with a circle. And so I'd say by that, given that both of these, it's just a replacement of a variable and just a different way of plotting different points, that this and this, or this are exactly the same.